This is a fairly lengthy video because it actually combines two topics, but it makes sense to look at C2.1 and 2.2 together. So feel free to pause the video and maybe go away and look at something else and come back to it. If you feel like you're not quite taking it all in, do just pause. In structure and bonding, you look at three different types of bonding. So you look at ionic bonding, you look at covalent bonding, and you also look at metallic bonding as well. We're going to do a quick introduction to each of them and how they work. For your ionic bonding, the clue is in the name, it's actually bonding between ions. And you're expected to be able to show, to represent the electronic structure of the ions. So electronic structure, remember, is showing those shells with those crosses with those electrons in them. And you have to be able to take the electronic structure of the atom and think, how has it changed to get to the ion? Something like sodium has actually got 11 electrons. The atom of sodium will give away that one outer electron to become that sodium plus. Whenever something loses an electron, it becomes more positive. The electron was negative and that's gone now, so that is why it has become more positive. And all you do is just represent it in the same way. If it had 11 electrons and it's lost one, it's now got 10 electrons left. Don't forget to put these brackets around it as well, and don't forget to show the charge. It's really important to show the charge on your ion. If it's lost an electron, it'll become positive. If it's gained a negative electron though, it'll actually become more negative because the electron is negative and that's being added to the ion. Covalent bonding is slightly different. With the ionic, we talked about atoms gaining and losing electrons and that making them positive or negative. Whereas in covalent, what actually happens is that electrons are shared. So in this example, you've got your nitrogen, and the electrons from nitrogen are shared with the electrons from hydrogen. Similarly, in your NH3, you can represent it like this, with your electrons from your nitrogen and your hydrogen being shared. The aim is always to try and get a full outer shell when you're doing bonding. So they might share electrons to get a full outer shell, or you might gain or lose electrons to get a full outer shell, like in your sodium ion. Be careful because the covalent bonding actually splits up into two different types of covalent bonding. Anything that's a small molecule like water, ammonia, which is NH3, hydrogen, which is H2, hydrogen chloride HCl, methane, CH4, and oxygen O2, is known as simple covalent bonding. They're simple molecules, they're small molecules. But then we also have these giant structures, things like diamond and silicon dioxide. So it's really important to look at those specific examples of those giant structures. You also have to learn about their properties, which we'll discuss later on. Your third type of bonding that you're supposed to know about is metallic bonding. And this is similar to ionic because you still have positive ions, but be really, really careful because actually in metallic bonding, you've got delocalized electrons. You've got your negative electrons and they're free to move around in between these positive ions. So ionic bonding is the attraction between positive ions and negative ions, but metallic bonding is the attraction between positive ions and negative electrons. So just be really careful that you're clear on the difference between the two. So we've talked about the three different types of bonding: ionic, covalent, metallic. And whenever bonding happens, you make something called a compound. So if you have bonding between two different elements, you will make a compound. And that'll either have been done by transferring electrons, so that'll be making a positive ion, making a negative ion, maybe having those free electrons travelling around in a metal, or it'll be done by sharing electrons like in your covalent. And we mentioned this before, the reason why things bond is to try and achieve the electronic structure of a noble gas. Put simply, that means you're trying to get a full outer shell so that the atom becomes stable. It doesn't want to react anymore. Remember, we said that any atoms that lose electrons, the negative electrons, will become positively charged ions. Any atoms that gain electrons, gain those extra negative electrons, will become negatively charged ions. And they will have the electronic structure of a noble gas. It's coming back to this point again here. It will try to achieve a full outer shell so that it is stable. Looking at the periodic table, anything that's in group 1, also known as the alkali metals, will actually form a 1 plus ion. So that's nice and easy to remember. Group 1 loses 1 electron, becomes 1 plus. And they will actually react with non-metals. So you'll have a reaction between the group 1 metal and a non-metal to form an ionic compound. An example of a non-metal is something maybe in group 7, because they have 7 electrons in the outer shell, and they will actually gain 1 electron, so they become an ion with a single negative charge. We call these the halide ions, so things like your fluoride, chloride, bromide and iodide ions, they're all 1 minus, F minus, Cl minus, Br minus, I minus. All of those have a single negative charge, and they could react with something like the alkali metals, which are 1 plus, to make an ionic bond. So the 1 plus is attracted to the 1 minus. We've mentioned that when your ions are formed, some are going to be positive, some are going to be negative, and the positive ones are going to be attracted to the oppositely charged negative ones and vice versa. And that means that in an ionic compound, you actually make something called a giant structure, a giant lattice made up of ions. And they're held together because of these attractions between the positive and negative ions. So it's held together because of these strong electrostatic forces of attraction. Electrostatic just means between positive and negative, between oppositely charged ions. And that attraction, strong electrostatic attraction between the positive and negative ions, is our ionic bonding. Moving on to the second type of bonding, covalent bonding, we said that this is where electrons are shared. Specifically, a pair of electrons is shared. And the bonds between the atoms are really strong. So you have strong covalent bonds holding the atoms together. We said about there being a difference between simple molecules and giant covalent structures. Make sure you know examples of both. Your simple molecules, things like H2, Cl2, O2, HCl, hydrochloric acid, H2O, water, NH3, ammonia, and CH4, methane. Check you can recognise both the formula, like it's written here, and the name, like it was written at the start of this. Your third type of bonding, remember, is the metallic bonding. And again, metals are a giant structure of atoms arranged in a regular pattern. So just like the diagram you saw at the start, those ions are arranged in a nice neat pattern in those rows, and then they've got the electrons being delocalized. You can also call them free electrons. They're free to move through the whole of the structure, the whole of the metal. And those electrons actually come from the outer shell of those metal atoms. So if you have a metal like sodium that has 11 electrons, 2 in the first shell, 8 in the next shell, and 1 in the outer shell, that 1 electron is free to move between the positive ions. So your metallic structure is positive ions with free electrons moving between the ions. And those electrons and positive ions have strong electrostatic attractions between them. So strong attractions between the positive and negative. Just like in your ionic bonding, you have the electrostatic attraction between positive ions and negative ions. In your metallic bonding, you have electrostatic attraction between the positive ions and the negative electrons. Make sure you're clear on the difference. Ionic between ions, metallic between ions and electrons, positive ions and negative electrons. So C2.1 looked at our three types of bonding: ionic, covalent, which can be split up into simple covalent and giant covalent, and metallic. C2.2 really closely links to C2.1 because it's now starting to explain some of the properties and uses of our ionic, covalent and metallic structures. Our simple molecules, these simple covalently bonded atoms, are often gases, solids or liquids that have relatively low melting and boiling points. The reason why they have low melting and boiling points is because these simple molecules, for all the atoms within them, are bonded together with strong covalent bonds. Between the molecules, there are only very weak forces. We call these weak intermolecular forces. And when you melt something or boil it, you're actually pulling the molecules apart from each other. You're not breaking the covalent bonds, you're pulling the molecules apart. You're overcoming these weak intermolecular forces. This is one of the things that students most commonly get wrong in bonding. So check that you know for simple molecules, things like the methane, the water, the H2, the HCl that we looked at previously, they have strong covalent bonds between atoms and they have weak intermolecular forces between the molecules of the substance. So an example of this is in oxygen, where you have strong covalent bonds between the oxygen atoms to make O2. And then between every O2 molecule, you'll have weak intermolecular forces. And it's those weak intermolecular forces that you're breaking apart when you melt or boil something. You're spreading out those molecules of O2 going from a solid to a liquid to a gas. So as you change from your solid to your liquid to your gas, what you're actually doing is you're breaking those weak intermolecular forces between the molecules. You are never breaking those strong covalent bonds between the atoms though. It's just pulling apart the molecules and breaking those weak intermolecular between the molecule forces. Knowing about melting points and boiling points is one property of simple covalent. The other property you need to know about is the fact that they do not conduct electricity because the molecules don't have an electrical charge. For something to conduct, it's got to have charge. You've got to have something that can carry the charge and make the flow of charge for your electricity. Just going to skip ahead in the specification to the giant covalent structures. It makes sense to think about our simple covalent and our giant covalent at the same time. You have three examples that you need to be aware of. We mentioned diamond and we mentioned silicon dioxide already. The third one you need to know about is graphite. They're all examples of giant covalent structures or giant covalent lattices. And you've got lots and lots of strong covalent bonds linking those atoms together in these three examples of giant covalent structures. All three of these structures have lots and lots of strong covalent bonds holding the atoms together. If you have lots of strong covalent bonds holding atoms together, that means you're going to need a lot of energy to overcome these bonds, and that means your giant covalent are going to have very high melting points. This is different when we're talking about the simple covalent ones. Here, we are actually talking about breaking those covalent bonds between atoms, whereas with the simple covalent, we talked about overcoming the intermolecular forces between the molecules. In diamond, every single carbon has 4 other carbons attached to it. So 1, 2, 3, 4 other carbons attached to it. Because you've got, again, lots of strong covalent bonds, that means that your diamond, a property of diamond is that it's very hard. In your graphite, it's slightly different. You've actually only got each carbon bonded to 1, 2, 3 other carbons. And that's again a really common exam question. They'll ask you for the differences between diamond and graphite, or they'll ask you to describe the bonding in diamond or graphite. Diamond has 4 bonds to every carbon, graphite only has 3. And because graphite only has 3, that means that there's actually 1 electron left. So carbon can form 4 bonds. It has got 4 electrons in its outer shell. So 3 of those electrons in the outer shell are used for bonding to other carbons in graphite, and that 1 electron left over is delocalized or free to move. And that free electron can move and it can conduct both heat and electricity. The other thing to spot in your graphite structure is that actually it's arranged in layers, and so these layers can slide over each other, and that's why things like pencil, which have graphite in them, can write on a page, because as you write on the page, a layer of graphite is coming off onto the page, or several layers of graphite is coming off onto the page. These layers can slide over each other because there aren't any strong covalent bonds between them. Instead, it's actually weak intermolecular forces between the layers. So like we had between the O2 molecules in the previous example, you've also got these weak intermolecular forces between the molecules, between the layers of graphite. And that gives it the property that it's soft and slippery, and hence you can write on a page with a graphite pencil. For higher tier, you also need to know that something called fullerenes can be formed from carbon atoms covalently bonded together in a giant structure. You can also make nanotubes, and these, again, as I said, are just examples of giant covalent structures made out of carbon. Just like in your diamond, all you have is carbons bonded together. In your graphite, all you have is carbons bonded together. Fullerenes, carbons bonded together. Nanotubes, carbons bonded together. You've also got something called graphene, which is a single layer of graphite that's quite a new material. And these new materials are really useful. Fullerenes have been used for things like drug delivery into the body, so they're used in medicine. They're used in lubricants for making machine parts move more smoothly. They're used as catalysts to speed up reactions. And you can also use nanotubes for reinforcing materials, so making things stronger. In the spec point here, it says that these fullerenes are based on a hexagonal ring structure of carbon atoms. If you look at the shape, you can see this one is actually an example of where they've got a pentagon, but you can get hexagonal ones as well. So like in your graphene, you can see here that's a hexagon shape, and in your nanotube as well, you've got the hexagon shape that all the carbons are bonded together as. Even though it's a hexagon shape, just be careful, each carbon is actually only bonded to 3 others at any one time. Now that we've looked at covalent in terms of simple covalent and giant covalent, let's come back to the ionic compounds. We said that the ionic compounds make giant ionic lattices because there are strong electrostatic forces. These strong electrostatic forces are the attraction between positive and negative ions. Because they're so strong, that means that the compounds are going to have high melting points and high boiling points, because you're going to need a lot of energy to break the many strong bonds, the many strong ionic bonds. So just like in your giant covalent, lots of strong bonds, it's going to take a lot of energy to break them, and therefore you're going to have high melting points and high boiling points. What's interesting about your ionic compounds is that if you dissolve them in water, these ions then spread out. And if the ions spread out, then that means that they're free to move and they're free to conduct electricity and carry the current. So this could be that they are dissolved in water and they are therefore free to move and free to carry the charge. Or if you melt them and turn them from a solid into a liquid, then again those ions are free to move and they can carry the charge, carry the current. Coming back to the third type of bonding, metallic bonding, remember what that structure looks like. You have your positive ions and you have your negative delocalized or free electrons that have come from the outer shell of those metal atoms. I've said it before, but just be really clear on the difference between your ionic, that is positive and negatively charged ions attracted to each other, and your metallic, that is positively charged ions and negative electrons attracted to each other. This electrostatic attraction between positive and negative is what bonds them together. That's your metallic bond. Because the metals have these delocalized electrons, these free electrons, they can carry the charge, and that means that metals can conduct heat and electricity. So just like in your graphite where you had the free electrons, they're able to conduct heat and electricity. Same is true for your metals as well. In your ionic substances, it's the ions that carry the charge. Metals is electrons, ionic is ions. The other thing you need to know about metals is that because they're arranged in these nice neat rows, those layers, can slide over each other. And that means that our metals can be bent and shaped. They are malleable is the other word that might be used to describe that. The fact that the layers slide over each other and therefore your metals can be bent and shaped, they are malleable. Sometimes you might want a metal to be able to be bent and shaped. Other times you might want something a bit stronger. And that's when we start to use something called an alloy. Alloys are a mixture of metals. They're made from two or more different metals. And the different size atoms of those metals, so here's one type of metal, here's another type of metal, actually distort the layers in the structure, so it changes the layers. It stops them being in such a neat, uniform order, and that actually makes it much harder for those layers to slide over each other. So if you look at this example here, it wouldn't really be that easy for these layers to slide over each other because of that distortion, because of that change in the shape. And that means that your alloys are much harder, they're much stronger than your metals. There's something that you need to know about called a shape memory alloy, and those shape memory alloys can actually return to their original shape after you've bent them or after you've deformed them. So something like if you've got braces, the point of your braces is to align your teeth in a certain way, and so the shape memory alloy in your braces will try and go back to its original shape and pull your teeth with it. Last few bits of this topic are to do with polymers and nanoscience. If you've forgotten what a polymer is, go back and look at your core science and check what a polymer is, because the properties of polymers depend on how they are made and the conditions under which they are made. So you get two different types of polyethylene. So polyethylene is the stuff that your plastic bags are made out of, and you can get low density polyethylene, so where there's not very many particles in a given space, and high density polyethylene where there are lots of particles in a given space. And to make those two you need to use different catalysts and different reaction conditions, like different temperatures, different pressures. The other two types of polymers you need to know about are thermosoftening polymers and thermosetting polymers. A diagram like this is often used to show the difference between thermosoftening and thermosetting. Your thermosoftening has individual tangled polymer chains. So the polymer chains are by themselves, but they're all tangled together. Thermosetting polymers have polymer chains that have something called cross-links between them. So these are like extra bonds between the polymer chains. And that means your thermosetting do not melt when they're heated. So they're set in shape. They do not melt when they're heated. Whereas your thermosoftening ones, when they are heated, they will softening. The other ones, thermosetting, when they are heated, they are still set in place. It says you need to be able to explain their properties in terms of intermolecular forces. So you have these cross-links, the bonds between the polymers. That makes it a lot stronger. It makes it that it will be set in shape. Whereas your thermosoftening, you just have weak intermolecular forces between the polymer chains, just like you have between the layers in graphite or between the individual molecules in something like ammonia or methane. That's what they mean when they talk about intermolecular forces. Here they're talking about the forces between the chains of polymers. When we talk about nanoscience, we're talking about structures that are really, really tiny. In the exam, if they ask you what nano means or what nanoscience means, it's not enough to just say small. You have to say that these are structures or these are things that are really, really small. We say that they're 1 to 100 nanometers in size, where a nanometer is 1 times 10 to the minus 9 meters. And so they might just be a few hundred atoms large, these structures. And these nanoparticles have very different properties to the same materials, to the same chemicals when they are in bulk, when there's lots of them together, so when there's obviously more than a few hundred atoms. Anything that is nano or nanoparticles will have a high surface area. It's like a very, very fine powder, so there's a huge surface area. And that means that we're able to use them to do really interesting developments in science and technology. So things like developing new computers, new catalysts, new coatings for things. So covering windows, covering glasses, all these kind of things, making highly selective sensors, making things that we can build with that are stronger and lighter. And especially in things like suntan creams, those nanoparticles block out the harmful rays. And we're also using them in deodorants. There are concerns around it because they're so small that people are perhaps worried they might be able to get through your skin. However, it's worth balancing concerns like that against evidence that have been produced for how useful these new materials are.